Okay, this is a short tutorial just to help you understand the concept of pulleys. So we're going to use this in the context of something called the Smurf problem. Now, when working with pulleys, there's a few assumptions we have to make in order to make the calculation simpler. One of the biggest things here is it said consider the situation where you've got three Smurfs, as you can see here, and these three Smurfs are being held on this pulley, and the system's going to accelerate. Most likely this side's heavier and is pulling down, and then this side is lighter, which will accelerate upwards in that direction. One of the assumptions we have to make for this, and this could be a good exam question, is that basically we assume that the ropes that contain these things are massless. Okay, so that's one big thing. The rope must be massless, or close to being massless, and it's free to roll over a frictionless, massless pulley. Okay, and it's suspended at some point. Now, we need to discuss quickly why this might be. The reason why we have to assume a massless system when trying to figure out what the acceleration of the system is because the mass of the rope, if you have a long bit of rope here and less rope here, then the mass of the rope will actually contribute to the acceleration on this side. So as the rope gets longer and longer and this rope gets shorter and shorter over here, you'll notice that this acceleration will change. So the acceleration will actually increase. And when you have a changing acceleration, this becomes a fairly more involved calculus type problem. So we're going to assume that the rope is fairly massless, meaning that even if there's 5 meters of rope on this side and only 5 centimeters on this side, it doesn't pull harder, causing this increase in acceleration. We want to assume that it's going to be a uniform, constant acceleration at this point. The other thing is that it's free to roll over a frictionless, massless pulley. Now, the reason for this is that we want no friction so that when we calculate the acceleration, we don't have to account for the internal friction in here, which would be, again, a much more complicated problem. We'd have to involve energy conservation and a bunch of other things as well. And the second thing is that we assume that it's massless. The reason why we have to assume it's massless is because, and we haven't really talked a lot about this yet, but if you take an object like a ball or a cylinder and you roll it down an incline, it turns out that when we talk before about, gravitational energy converts into kinetic energy, well, that's true for objects that are sliding or where there's not a significant amount of rotation. But however, when you have an object if it's significant mass and a significant radius, when it rolls down a hill or when you try and spin this object, some of the energy actually has to go into what's called rotational kinetic energy as well as translational. So what's happening is as we accelerate this pulley, it actually takes energy to accelerate it, and therefore the acceleration that we get for the system would actually not be constant, and it would be much more complicated to solve if this had a defined mass. So we'd have to figure out the moment of inertia and to figure out how it's truly accelerating as part of this whole system. So when rolling a ball down an incline, we would find that the object at the bottom of the incline isn't moving as fast as it should, based on purely gravitational energy being converted to kinetic energy, because what happens is some of the energy is converted into rotational energy and kinetic energy. So if you have 100 joules going in of gravitational, then at the bottom you might have 80 joules of translational kinetic energy and maybe 20 joules of rotational energy. So if we assume in terms of the system that the pulley is frictionless and massless, then we don't have to worry about that situation. And if we assume that the rope's pretty much massless, we also don't have to account for the amount of rope that's on this side compared to that side. And if these objects here are massive enough, then that's a good approximation. So again, our work here, based on these assumptions, imply that our value, our acceleration, is an approximation. And depending on how good how frictionless and how light you can make the pulley and how light you can make the rope compared to these other objects, this assumption will hold truer or less true depending on the situation. Alright, so all we're trying to do is figure out what the acceleration of this object is. I'm not really too concerned about the masses right now. We can plug in masses later and just make up a value, but what we want to look at is, can we figure out what the acceleration of the system is? So some key things. One thing we're going to look at here is, since these two objects here are likely more massive, we're going to assume that the rotation or the acceleration of the system is in this direction. This object will accelerate up, so I'll make that direction positive. Will accelerate upwards, while this side of the system will accelerate downward. We'll see how important that is afterwards. What we're going to need to do to solve this is we need to write a Freebody diagram for Brainy Smurf, Papa Smurf, and Smurfette right here. So we need to draw the Freebody diagrams for each of those and talk about what we notice. Now before we go too much further, there's one other thing, there's two more concepts that are big for pulleys. One of these is that when these two objects are connected, we can see that they're connected by a rope, like this. Now, that means, if we remember Newton's third law, we say that for every action there's an equal and opposite reaction. It means that the forces pulling on this are the same as the forces pulling on this. So the tension in this rope is the same for both objects. That is a fundamental, very important part of this problem solving. So that means that if we look at the tension in this rope, which is the tension between Smurfette and Brainy Smurf, objects 1 and 2, it will be the same as the tension over here. Exactly. Here, the tension pulling down on Brainy Smurf is the same as the tension pulling up on Papa Smurf. Like so. So that whatever tension in this rope, it's pulling down on Brainy Smurf, and we'll call it T12, and it's the same as the tension pulling up on Papa Smurf, which is also T12. So the tensions in the ropes between two objects are the same. You can imagine if you connect the two together by making that rope infinitely smaller, and just smaller and smaller and smaller until they touch, you can see that the force between them must be the same. Alright, so let's look at the free body diagrams for these, the FBDs for this system. Okay, free body diagrams. Okay, we'll start with Smurfette. She's probably the easier one to deal with. So that's object 3. Now, object 3, if we look at this, we realize quickly that M3 is the mass. I think everyone can agree that one force acting on her is just the force of gravity, calculated as the mass times the acceleration of gravity. And that there's also a tension pulling upwards, which is accelerating her in the upwards direction. Okay, so we'll leave that one for now. Now let's do Papa Smurf, number 2. Papa Smurf has gravity pulling down on him, and tension that's going to be smaller because he is accelerating downward, of T12. Brainy Smurf, a little different here for Brainy Smurf, M1. Brainy Smurf has the T1, sorry, I messed up at the beginning. This is T13. So you probably recognize that right at the beginning, that should have been T13. Here we notice that Brainy Smurf has T13 acting on it, has gravity pulling down, M1G, and there's also the tension pulling down. So this Brainy Smurf here has multiple forces pulling on it. Gravity, the tension of Papa Smurf hanging on to him, which isn't equal to his weight. If they were stationary, yes, then T12 would just be the weight of Papa Smurf. But because they're accelerating down, he's going to appear lighter. And if they were falling in free fall, he would appear not to even be any tension here because they'd both be falling at the same rate, which we know from before. Okay, the next step to solving this and figuring out what this acceleration is writing our system of equations. And the system of equations works like this. For number 3, we're going to write, we chose up as positive from this, so it's going to be T13 minus M3G equals M3A. Newton's second law. This came from sigma F equals MA. And that's it. I just applied Newton's second law. I'm just going to leave some space here because this next part is going to become important. 2. In this case, we chose this way as positive for these two objects because they're accelerating in the downward direction. So in this case, I have M2G minus T12 equals M2A, again from net sigma F equals MA. The third one is T12 plus M1G minus T13 equals M1A. Okay. Now, there's some unknowns here. We know the acceleration of the system is all the same. So this acceleration is the same as that acceleration, is the same as that acceleration. We know that T12 matches up with T12, and T13 matches up with T13. So what we do is we take this equation here and we isolate for T13. Take this equation here and we isolate, so I have to switch the signs here. This is going to have a negative in front of it. So I have M2A minus M2G, like that. Just bring it over. So that implies that T12 equals M2G minus M2A. I just switch the signs. I moved them a little bit. So now we have this equation, and we have this equation. We have T13 written in terms of the values that we're going to know, and T12 written in values that we're going to know. Now what we can do is just simply substitute these values in. So T12, so what we're going to do here is substitution. Like so. And what we get is M2G minus M2A, M2A, this is our T12, plus M1G minus M3A plus M3G, like so, equals M1A. We can do some minor simplification here. Just write M2G minus M2A plus M1G minus M3A minus M3G equals M1A. At this point, I'm not going to solve the rest of it for you. You're going to solve it on your own. What you're going to notice is that you want to take everything with the A, these two here, and add them to this side. And the stuff with the M2G plus M1G minus M3G, leave it on this side. Common factor out the G. On the other side, common factor out the A. Do a simple simple rearrangement at that point, and you'll find an equation for the acceleration quite simply. Okay, so I'll leave that up to you, and then you can show me your solution for that.